Hello and welcome friends. The particulate pollution is important aspect in air pollution and control. The particle could be removed from the gases stream through the natural gravity settling. In order to do so, we have to have knowledge about their settling velocity. In this presentation, we'll discuss about the determination of settling velocity by Stokes law, applicability of the Stokes law for range of the particulate, and necessary corrections for the size of particulate which do not fall within the range of the assumptions Stokes has made while devising the expression for terminal settling velocity. You already know that the particles could be referred as discrete particles as well as flocculating particles. Discrete particles are those particles which do not alter their size, shape as well as their specific gravity. For example, fugitive road dust. The flocculating particles change their size as well as shape, and even as they coalesce together, their specific gravity could also be changing. Say, for example, we can think about certain, say, particles, which is particles which are creating certain fog, mist, spray, and similar ones. These particles could be existing in dilute form, say for example, natural air breeze, or they could be in concentrated suspension, for example, emission out of the stack. In general, the particulate range could be 0.001 to 500 microns, whereas the bulk of particulate could be in between 0.1 to 10 micron size. In order to have this particulate range, there could be man-made sources such as industry, or there could be certain natural sources such as volcanic eruptions. For air pollution and control, we mostly deal with particulate range 0.01 micron to 10 micron sizes. Even this kind of particulate range can be further divided into coarser, finer, as well as even certain ultra fine ranges. We have had this kind of a discussion in another presentation. The particles which are having sizes less than 20 micron size behave almost as that of the gas stream, whereas the particulate which is having size more than 20 micron have significant velocity, and we need not bother much as far as air pollution and control is concerned. The particulate which are having the another classification, say for example, inhalable or respirable, need to be collected through the control devices. There are a lot many control devices in order to establish the control on the particulate. These devices are expected to collect the particles through their movement in the gas stream. In order to have them captured, the particle must be subjected to the external forces large enough to separate it from the gas stream. Hence, we must know about the kind of the forces that are acting on the particle when the particle moves through gaseous stream. In general, we can have these particular forces defined as gravitational force, which is given by rho p into g into Vp, where that rho p is particulate density, g is gravitational acceleration, Vp is volume of the particle. The second force which is acting on the particle is buoyant force, which is given by rho w times gravity into volume of the particle. The drag force is given as CD times AP into rho w into V square by 2. Here, this CD is nothing but coefficient of drag. AP is the cross-sectional area of the particle perpendicular to the direction of the movement, and small e is velocity of the particle. In addition to gravitational force, buoyant force and drag force, there could be even other forces such as magnetic, inertial, electrostatic as well as thermal forces. The terminology of these particular forces and their action is shown through this particular schematic sketch. The resultant of the acting forces on such a particle is nothing but the settling velocity. The terminal settling velocity is constant value of the velocity reached when all the forces, as shown in the previous slide, acting on the body are balanced. That is, when the algebraic sum of all these particular forces is equal to 0, that is, there won't be any further acceleration. In order to know the particle settling velocity, there is a necessity to know through which flow region the particle is moving. That is, whether the particle is moving through laminar stream, is it moving through transitional stream, or it is moving through the turbulent stream. Once the flow regime is defined, we can calculate the settling velocity of the particulate. Stokes' law is helpful to determine the terminal settling velocity of the particulate. Stokes' law is mathematical expression used to calculate the terminal settling velocity of airborne particulate. The equation takes into account the gravitational as well as drag forces acting upon the particulate. The equation can be used to calculate the terminal settling velocity through the well-defined assumptions that Stokes made. These are mentioned as follows. The first assumption is the fluid through which that particular particulate is moving is continuous. The flow is laminar. the nature of the particulate is assumed to be spherical. The medium is homogeneous, that is, it is uniform in composition. The conditions of settling are quiescent. There is absence of turbulence such that the particles do not interfere with each other. For particles which are either very large or very small, which do not follow the assumptions made here, we cannot make use of Stokes' law directly applicable for the determination of terminal settling velocity. Let's try to devise the expression for Stokes' law through these couple of slides. Here, what you see is spherical particle settling through fluid under gravitational force. It is also experiencing the drag force and buoyant force in the opposite direction. Here, the terms on the left hand side represents the downward acceleration of the particle, whereas the terms on the right side are showing the forces, the force due to gravity, the force due to buoyancy, and the drag force. Initially, when the particle is at rest, that is, when its velocity is zero, it does not have any drag force. But as the particle start moving in the downward direction, it accelerates and even the drag force goes on increasing until it equals the difference in between the gravitational force and the force due to buoyancy. Hence, Fd equals Fg minus F buoyancy. So accordingly, here we get this particular expression. At this instant, particle continue to move at constant velocity, which is called as terminal settling velocity. Stoke has determined mathematically the value of drag force, and it is given by 3 pi mu dv. Here mu is viscosity of the fluid, capital T is diameter of the particle under consideration. So, as we compare this particular 3 pi mu dv term in this particular expression, what we get is V is given as gt square into bracket rho particle minus rho fluid bracket complete divided by 18 mu. Here, as we are dealing with air, rho fluid is nearly 1 and it can be easily neglected. So, the resultant expression can be considered as V is equal to GD square rho P divided by 18 mu. Let's make use of this Stokes expression to compute the terminal settling velocity of a sphere with diameter 1 micron. So you have the device expression V is equal to GD square into bracket rho particle minus rho fluid divided by 18 mu. Here, let's take into account the properties of the air as well as the particle under consideration, and let's substitute these values in this expression. G is gravitational expression 9.81 meter per second square. The particle diameter as given is 1 micron, that is 10 raised to minus 6 meters. Rho particle is 2000 kg per cubic meter. Usually this value ranges in between 2000 to 2500 kilogram per cubic meter. As said previously, as we are dealing with air and as the value is nearly 1, as you see here it is 1.20 kg per cubic meter, but as compared to 2000 to 2500 kg per cubic meter, this value is quite negligible. It won't affect the result considerably. Mu is the viscosity of the air, which is given as 1.8 into 10 raised to minus 5 kg per meter per second, and as we substitute these particular values, the resultant that we get is 6.05 into 10 raised to minus 5 meter per second, which is nothing but terminal settling velocity of this particular particle. As you know, in the absence of any another suitable expression, Stokes' law is widely used in the field of water, wastewater, as well as even air pollution, in order to determine the settling velocity of the particulate of the size range of the interest of that particular relevant area. It has been well verified for the range of the conditions in which the assumptions on which it is best hold good. In general, it is quite accurate for the spherical particles with a diameter less than 50 to 100 micron. As in air pollution, we are expected to deal with particulate size range of 0.01 micron to the bigger sizes. We have to compare the assumptions made and its real applicability while determining the settling velocity of the particulate. For the particulate which are very coarser and which are very smaller, the assumptions that have been made do not hold good, and the Stokes' law cannot be directly used in order to determine the settling velocity. This particular diagram is depicting terminal settling velocity for the spherical particles with specific gravity 2 in standard air. On horizontal axis, what you see is nothing but particle diameter, whereas on vertical axis, what you see is terminal settling velocity expressed as centimeter per second. Here, in between these two curvilinear portions, what you see is nothing but straight line. This is the region wherein we can directly make use of Stokes' law. Beyond this particular diameter, the particles are larger in diameter, the flow becomes turbulent, hence the quiescent conditions that are assumed while devising the Stokes law are not applicable. Hence, there is a need to consider some correction factors in this region where the particles are having larger diameters. In a similar manner, in the lower region, what you see is nothing but the particles which are having less than 1 micron diameter. The particles are having smaller diameters, and herein we cannot make use of Stokes' law directly applicable in order to determine the terminal settling velocity. There is a necessity to apply the correction factor, which is called as Cunningham correction factor. In coming slides, we'll discuss both the approaches that should be followed for the smaller particles as well as for the larger particles. For larger particles, the flow about the larger particles becomes turbulent, and quiescent conditions assumed by devising Stokes' law do not remain valid. Though efforts are made to devise simple expression similar to Stokes' law, the results are not satisfactory, as for larger particles no theoretical formula represents experimental data over more than modest range of the values. In order to determine the settling velocity for the particles which are too large for Stokes' law, we make use of two basic expressions. One is drag coefficient and second one is Reynolds number as given on this particular slide. The Stokes drag term can be substituted and the result can be rewritten as CD is equal to 24 by RP. The process is elaborated here. You have the expression for CD, you have the expression for FD. As you substitute these 3 pi unit dV for this particular FD and make use of value of expression for Reynolds number RP is equal to dV rho f upon mu, you will get CD is equal to 24 by RP. Experimentally, it has been found that Stokes' law represents the observed behavior of the particles satisfactorily for Reynolds number less than 0.3. For the values 0.3 less than equal to Reynolds number less than equal to 1000, the experimental drag coefficient can be represented with satisfactory accuracy with this particular data fitting equation. We'll make use of some example in order to elaborate further discussion. Here, we wish to determine the settling velocity of a particle which has 200 micron diameter assuming that Stokes' law is valid. For that case, we wish to determine the Reynolds number. Now here, as we determine the settling velocity by using the expression v is equal to jd square rho p upon 18 mu that you deduced as Stokes expression, you will get the settling velocity of 2.42 meter per second. Whereas, as we try to determine this particular Reynolds number for this particular particle, what we get is 32.3. Here, it can be easily concluded that this result is clearly greater than the Reynolds number of 0.3, which is normal upper limit for the reliable use of Stokes' law. Hence, we have to go for revised calculations. In order to determine, or rather in order to estimate the true settling velocity for such larger particles, we have to go for various trial and error steps. Here, I have attempted to elaborate the steps involved in this particular slide. Let's try to understand that. Here, the step 1 is determination of settling velocity by making use of Stokes expression, assuming that the assumption hold good for the particle under consideration. As we determine the settling velocity, let's calculate the Reynolds number. If the Reynolds number is more than 0.3, that means the settling velocity that we have calculated is not appropriate for the given conditions, and it should be estimated by using the following steps. So here the step 3 tells us to determine the coefficient of drag. So here we can make use of that data fitting equation, the one that we considered on previous slide. Here, as we have the basic expression CD is equal to FD by pi by 4 d square rho f v square by 2. Here we can solve this for settling velocity by substituting the value of FD as pi by 6 dq rho p times g, and we can get the expression shown here. Now the next step is by using this Vt calculated, we can determine the value of Reynolds number, and we can check the calculated Reynolds number with the value that is assumed in step number 3. So, as we get the Reynolds number in step number 5, based on the estimated settling velocity, we can recompute the coefficient drag, and we can further go for computation of estimated revised velocity. For that, again, we can determine the Reynolds number, and for this Reynolds number, we can determine further the coefficient of drag. Here we can reiterate these particular steps till we get the Rp nearer to the assumed value, and the corresponding velocity to that particular Rp can be considered as estimated true settling velocity. We can have this particular concept further elaborated through the example as discussed by N.D. Nevers in his book Air Pollution Control and Engineering, published by McGraw-Hill International Editions. So here It is expected to estimate the true settling velocity for the earlier problem, wherein the particle diameter was 200 micron, 200 micron. So, we have to follow here trial and error solution the way we discussed in the previous slide. We'll begin the computations by assuming Reynolds number to be 20. For that, we calculate the coefficient of drag. Here, what we get is 2.57. The way we discussed will work out the settling velocity expression by substituting the value of FAD the way we discussed in previous slide. So here what expression that we get for Vt can be substituted with the values in order to get the settling velocity as 1.3 meter per second. Now, as we have estimated this settling velocity, we must check our assumption that Rp is equal to 20. So using this value of the velocity, we find the value of Rp by making use of this particular expression as 17.3. Now, as we have the equation CD is equal to 24 by Rp into bracket 1 plus 0.14 R raised to 0.7 bracket complete. We compute that this corresponds to CD is equal to 2.82. Since the calculated Vt is proportional to 1 by CD bracket raised to 1 half, we can compute the new estimate of the terminal settling velocity as shown here. It works out to be 1.24 meter per second. Repeating the Rp calculation, we find Rp is equal to 16.5. For this Rp, we get CD of about 2.9, leading to new velocity estimate of 1.22 meter per second and new Rp of 16.2. At this point, we may consider the problem is solved because further cycles of trial and error will make changes in the answer smaller than our uncertainty in the drag coefficient correlation. So, based on this example, we can conclude that for 200 micron particle of specific gravity 2 settling in air at 20 degrees centigrade, the true velocity is only half of what we calculated by Stokes law. Only the thing is that this particular method is very tedious, as we have to go for number of reiterations as discussed in these couple of slides. It's better to use the graph as we discussed, showing one that terminal settling velocity for spherical particles with specific gravity 2 in standing air, in which that particular terminal settling velocity was shown on the vertical axis, whereas the particle diameter was shown on horizontal axis. Similarly, we have discussed about the Laplace chart, which describes the sizes as well as the characteristics of airborne particles. In addition, there are a number of graphical solutions available in the literature showing terminal settling velocity of the spherical particles of different densities settling in air as well as in water at 70 degree Fahrenheit under the influence of gravity. So here these particular kind of the graphical solutions will give us the ready-made solutions in order to get the relevant data. You could be remembering the graph that was showing terminal settling velocity versus particle diameter, in which the relationship was shown by some intermediate region valid for the Stokes region, whereas the upper curvilinear region, in which we have to incorporate the drag coefficient as well as Reynolds number in order to determine the settling velocity for the particles too large for Stokes law, whereas the lower region was showing the particles too small for Stokes law. So Stokes law assumes that the fluid in which the particle is moving is a continuous medium. When a particle becomes as small as or smaller than average distance between the molecules, then its interaction with the molecules changes. The effect of the change from specular to diffuse reflection is to lower the drag force, which causes the particle to move faster. In simpler terms, we can visualize the particle size is too small to have the hindrance through the molecules of the fluid through which that particular particle is moving. Obviously, as the particle does not have hindrance, it will move faster. The most widely used correction factor for this change is given by this particular expression, where this revised FD is determined by dividing FD Stokes by the term 1 plus A lambda by T. Here, A is an experimentally determined constant, lambda is mean free path, and capital D is diameter of the particle. FD Stoke is the drag force computed according to this particular Stokes law. The term 1 plus A lambda by D used here is called as Cunningham correction factor. Here, it is only applicable for values lambda more or less equal to particle diameter, so as to have lambda by D of magnitude 1. For much larger values of lambda by D, more complex formulae are used. So, in order to have the discussion more clearer, we'll attempt one example again with reference to Never's book. Here, you are already acquainted with the FD given by this particular expression, as well as pertaining to the involvement of Cunningham correction factor as we discussed in the earlier slide. The basic expression we use for drag force while devising Stokes law. So as we combine this, what we get is the revised velocity for the smaller particles can be determined by the product of V Stokes and the Cunningham correction factor. So here the particle size is 0.1 micron. It is settling in the still air. We wish to determine its terminal settling velocity. Here the constant that we discussed, A, can be assumed to be 1.728 as given by Millikan for oil droplets settling in air. Mean free path can be assumed to be 0.07 micron. So let's make use of this particular expression. For this particular size, already we have determined the settling velocity, which comes to be 6.5 into 10 raised to minus 7 meter per second. Let's determine the Cunningham correction factor. It comes to be 2.21, and hence here, as we make use of this particular expression, the settling velocity for the particle which is having the size 0.1 micron can be 1.34 into 10 raised to minus 6 meter per second. In addition to the Stokes approach, the correction for two large particles or the correction for two small particles, one more approach one can be used here. So this has the background of fluid mechanics. You could have discussed this. So here we wish to determine the flow regime first. So in order to determine that particular flow regime, here we can make use of this particular expression, in which here this k is a dimensionless constant which determines the range of fluid particle dynamic laws. Here this dp is particle diameter expressed in centimeters. Cap small g is gravitational force expressed in centimeter per second square. This is rho p, particle density, gram per cubic meter. This is rho a, which is nothing but fluid density, grams per cubic centimeter. Mu, which is fluid viscosity, grams per centimeter second. So if we work out this k by substituting the appropriate values less than 3.3, the region can be considered to be laminar. If the value of k works out to be ranging in between 3.3 and 43.6, the regime can be considered to be transitional. Whereas if this constant has the value more than 43.6, we can assume this region to be turbulent. So for respective laminar, transition and turbulent regimes, you are provided with various expressions which you can make use of for the determination of the terminal settling velocity. Here, as you refer to other literatures, you can get the similar approaches. For example, you can make use of the term coefficient of drag. So here already you know that if the CD works out to be 24 by RE, the region is laminar. Similarly, here if this particular coefficient of drag equals 24 by RE plus 3 by root RE plus 0.34, the region can be considered as transitional region. Whereas the CD has value of 0.4, the region can be considered to be turbulent. So such approaches we can come across through various literature, and accordingly we can determine the settling velocity for the particulate. So let's summarize the discussion that we had through this particular presentation. In the context of air pollution and control, particle may have lot many sources as well as their definitions. Even their behavior is different, as well as depending on their particular size, physical characteristic, chemical characteristic and behavior, it has different impacts on human body as well as property or in general atmosphere. Stokes' law is basic expression for the determination of the settling velocity and can be used with sufficient accuracy for the size range in the interest of air pollution and control. In addition, we can make use of coefficient of the drag or certain, say, the constant k, the way we discussed in the previous slide, and accordingly we can determine the settling velocities. Thank you.